Hello, I'm Soyoung Yun from Seoul National University, and I'll present our ACL 2025 work, RoToR, towards more reliable responses for order-invariant inputs. This is a joint effort with Seoul National University and colleagues at Channel Talk. The key theme is positional robustness. How can we keep large language models reliable when the order of parallel segments, rows, choices, facts should not matter? So the summary of the work is that we introduce RoToR, an attention-modifying method which ensures robustness to the ordering of list-wise inputs. I will first talk about the motivation, related works, contributions, and results. The take-home message is that RoToR exceeds SOTA robustness on various benchmarks with lower flops. Let's start with the motivation. The lost in the middle problem in RAG is that when you insert the relevant passage at different positions, GPT class models deteriorate heavily. Similarly, when we ask an LLM to be a judge, it chooses the first answer 75% of the time, a so-called first choice bias. The example figure on the upper right illustrates how the same red fruit question flips from correct to wrong purely by option order. For inputs where the ordering of segments is semantically irrelevant, for what we call list-wise inputs, we require the model to produce identical predictions under any permutation without fine-tuning and with minimal computational overhead. Prior works to mitigate this bias include self-consistency, which runs inference multiple times with different orderings of context. However, they do not scale well, requiring approximations. A more fundamental way to enforce invariance include PCW, set-based prompting, and Pine, which directly alters the attention mechanism in transformers in a zero-shot way. We'll first show you a brief example to show how prior works enforce invariance via altering self-attention. Let's say you were given the following input. A typical transformer decoder model will calculate self-attention in a causal, autoregressive way. To encode query token apple, it will only look at the prior key tokens, which is given and apple. For orange, it will contextualize with given, apple, orange, each assigned with a linearly increasing position ID of 1, 2, 3. And this goes on and on. Now, let's see how invariant models behave. For the prefix tokens that are not considered as list-wise segments, the behavior is the same as the original model. However, for encoding query tokens that are considered as list-wise segments, we first open all the segment tokens in the key token and enforce bidirectional attention calculation. Since positional bias is coming from two characteristics, the first one is the positional ID assignment, and the second one is the causal attention, so we need to mitigate these both. To align with the autoregressive nature, we enforce the position of apple as key tokens to be the last, which makes the ordering of key tokens to be changed as this way. Then we order the key segment tokens so that the ordering is not a function of the initial ordering of segments. So the ordering of orange, banana, and grape should not depend on the initial ordering, which was apple, orange, banana, and grape. In other words, the ordering between segments should be determined no matter what the initial ordering was. For Pine, they chose to use the attention values with positional IDs removed to get the invariant ordering. They compute pairwise attention among segments without positional ID and use that to order key tokens. Like this. This is repeated for all query tokens. However, this introduces some problems since we need an additional step to recalculate pairwise labels for every tokens. So, to sum up, Pine assigns the query segment to the end of the sequence, then orders remaining segments by similarity, which is computed by attention without positional IDs. However, prior works break in two ways. First, PCW and set-based prompting enforce invariance by isolating segments. This removes inter-segment attention and degrades accuracy. Pine retains attention but recomputes a query-specific position map, incurring additional big O of n squared operations and frequent position ID changes. Also, Pine is computationally expensive due to attention value computation without position IDs and it's numerically unstable in case we have ties, so we cannot fully guarantee invariance. Second, no prior methods investigate on or supports inputs that has both order-sensitive and order-neutral parts. For example, MMLU, a multi-choice question, has prompts like both A and B or none of these, where the option order is important and the order bias is needed. So we propose RoToR, which keeps the bidirectional structure but alters the position ID assignment by defining a single global ordering and circular assignment. Circular arrangement means that we keep the relative global order between segments, but shift so that we reuse that ordering all the time. How do we define global ordering? We can simply use hierarchical lexical sorting based on the encoded token IDs of each segment. Here, 16 is the maximal value, so apple becomes first, orange becomes second, and so on. Going back to the illustration for curry apple, we fix apple to the last and order key segments to follow the global order, which is orange, grape, and banana. And this goes on for orange, banana, and grape. As a result, we address both prior challenges. RoToR achieves invariance with a single global ordering and a circular position ID scheme, so they are more stable and exhibit less out-of-distribution behavior. For limitation 2, we propose selective routing, which compares confidence scores from the base model and its invariant model and routes to the more reliable answer. Comparing with Pine, RoToR removes query dependence. As a result, RoToR achieves stable ID assignment with 0 collisions and less computation. The illustrations show that Pine's position grids vary across heads, whereas RoToR's grid remains stable. Consequently, RoToR reduces additional computational overhead and narrows the train test distribution gap. For hybrid tasks that need selective routing, we compute the max token probability P for both models. If the probability of RoToR exceeds the ones on the original plus alpha, we select the RoToR answer as the final answer. Otherwise, we keep the original. We experiment with 4 benchmarks, 2 different backbones with various model sizes, and report results on various baselines, including the original order-sensitive variant, PCW, set-based prompting, Pine, and RoToR. Relative to Pine, RoToR cuts flops by 95 to 98% on QN 72 billion and reduces the end-to-end latency by 23 to 43% on lost in the middle. Collision rate of position IDs is reduced from 42% to 0%. We also measure the perplexity of Pine and RoToR. The perplexity of RoToR is lower, meaning that input representations are closer to in distribution. On the lost in the middle, RoToR, red raises the best subspan EM from 59 to 62% on Llama 8 billion and remains almost flat across all 30 passage positions, whereas the baseline, blue, fluctuates by up to 5 points. We observe similar trends across different QN and Llama with various model sizes. Results on RoToR remain stable and exceeds better exact match scores than the baselines. On results on the KGQA with 50 retrieved triples, RoToR improves F1 over Pine by 2.3 points on QN 7 billion and halves the standard deviation after shuffling segments. Gains persist across model sizes. For MMLU, RoToR alone scores lower than the original because some prompts are order sensitive. However, RoToR with selective routing restores accuracy to 68.5% on Llama 8 billion, matching the original while maintaining invariance over various order permutations. In summary, RoToR provides a training-free, computation-efficient path to order invariance in decoder-only LLMs. Selective routing extends the method to mixed input scenarios. The code and data are publicly released. This is the end of our talk, and thank you for your attention. One point to add is that there are some questions on the live oral presentation about the format, what kind of format can we do, and whether we would need additional splitting between which ones are the segments and which ones are the original prefix and suffix tokens. So this is the example of the real data set that we use. This is the example of the lost in the middle benchmark. We can see that parallel texts are annotated as document 1 and document 10. So in our experiments, we manually separated them with the document signal. But I think that we can also extend this method to splitting segments by automatically by such as new lines or like token lengths. I think this method can be extended to scenarios where we don't have prior information about which segments we can use. Yeah, thank you.